All right. Right. So the next concept we have in this is after this generalized heat conduction equation in three different coordinates, the next topic is boundary conditions. Boundary conditions. This is our next topic. See, till now we have considered a differential equation. Whatever the differential equation, whether it is in rectangular or spherical or cylindrical systems, that particular equation will be useful to you only if you have boundary conditions. If you don't have boundary conditions, you cannot apply that equation in the real case. So boundary conditions will help you in applying the given differential equation to the real case. Okay, so that is what the use of your boundary conditions. Coming to the boundary conditions, there are basically three primary boundary conditions. I write it like 3 plus 2. Some textbooks have 3 plus 1, some textbooks have 3 plus 2. Anyways, 3 is important, 2 is not so. Okay, so remember these three, that will be good enough for your syllabus, right? Mostly these three you will use in your syllabus. All the cases can be covered in these three. Okay, plus 2 are actually different cases which you will not be having it in your syllabus. So in this first one will be temperature boundary condition, or this is also called as Dirichlet boundary condition. Dirichlet is the man behind this temperature boundary condition. That's why you call it as Dirichlet boundary condition. The next one is heat flux boundary condition. Heat flux boundary condition, or this is also called as Neumann boundary condition. NUE, Neumann, N, Neumann boundary condition. The third one is, this is called as mixed boundary condition or convection boundary condition, or this is also called as Robin boundary condition. Robin is man behind this mixed boundary condition or the convection boundary condition. Here Neumann is the man behind the second kind of boundary condition, that is heat flux boundary condition. Okay, these are the three things that you will have. This is 3. Plus 2 is like the fourth one we will take, radiation boundary condition. The fifth one is conduction boundary condition. Okay, these are all the 5 things. First 3 are very important. Now look at the first one, that is temperature boundary condition or the Dirichlet boundary condition. What does this say? The temperature boundary condition will be giving you the temperature at boundaries. Okay, so in any given boundary condition, what you will do is you will get so and so parameter. In this case, it is temperature here. Let us consider a case here. It can be a simple wall case. It can be cylinder case. Anything. If it is giving, this will be the boundary. If it is giving you temperature at the boundary, that will be the temperature boundary condition. That is, I will take this simple case for your conduction in a wall. I have taken it like this. Okay, this is x is equal to 0 and this is x is equal to L. The thickness of this wall is actually L. That's why if I take it in x coordinate system, the x is equal to 0 is on this side, x is equal to L is on the other side. Now, here I want to define the temperature T1 on this side. On the other side, I want to define T2. I can measure this T1 here. I can measure this T2 here. In that case, the boundary condition will be like this. Yet x is equal to 0, the temperature is equal to T1. And at X is equal to L, the temperature is equal to T2. So this will be a temperature boundary condition in this case. It need not be a slab. It can be for anything for that matter. It can be for cylinder. Okay, you can take a hollow cylinder. If this is the case, no, let me write this one also. Okay. If I take a circle here, okay, this is having radius R1, this is having radius R2. There's a temperature T1 at this radius, temperature T2 at this radius. So if this is the case now, what I can write this temperature boundary condition will somehow to be like this. Yet R is equal to R1, temperature is equal to T1. Yet R is equal to R2, the temperature is equal to T2. So that's how we can write it for the sphere also. So that's how you will have the temperature boundary condition. Next one is your heat flux boundary condition or Neumann boundary condition. In this, what happens is if you take a wall here, this is x is equal to 0 and x is equal to L. So what you define here is heat flux. You will say that there is so and so heat flux Q1 here, there is so and so heat flux Q2 here on the other side. So how you write this is get x is equal to 0, Q is equal to Q1, you will write at x is equal to L, Q is equal to Q2, you will write. That's like same way you can write it for the cylinder and for sphere also. That is the heat flux boundary condition. And the third one is mixed boundary condition. Mixed boundary condition or convection boundary condition or Robin boundary condition. Okay. In this case, what happens is you have a wall here. This wall, this wall is having so and so atmosphere here. Because of this atmosphere, you will have convection present here. And in this particular solid, conduction happens. And we have seen that the conduction is predominant in solids and the convection is predominant with fluids. So here you have fluid, here you have conduction. This is fluid and solid you have here. And if you take the heat transfer at this particular point, here what I will define is Q convection is equal to Q conduction. I will take it. So this side I will get H into T minus T infinity I will get. On the other side, K into dt by dx I have taken. So that the area effect is not taken here. See, this is the area perpendicular to the direction of heat transfer with respect to conduction. And the same area is the area with which the fluid is interacting. So the area is same in both cases. So area can be taken out. And this is how you will get a boundary condition. And this boundary condition, where are you defining? This boundary condition you are defining at this particular surface. Okay, surface 1. Okay, you can take it like surface, get surface 1. Convection is equal to conduction. This is the third kind of boundary condition. And the fourth one is radiation boundary condition. It is similar to the convection boundary condition. You will have the same thing here. This is very long wall, and here radiation is happening on this side. Here conduction is happening. Now, if you take this surface 1 here, at surface 1, Q radiation is equal to Q conduction. So what you will take is sigma into epsilon into t to the power of 4 minus t to the power of 4 is equal to conduction is k into dt by dx will have. So this will be your radiation boundary condition, similar to your mixed boundary condition or the convection boundary condition. And then this one is conduction boundary condition. Conduction conduction boundary condition. Here what you have is, here you will have two materials. Okay, this is material 1, this is material 2. Okay, uh, then here you have a surface. Let me call this surface as A. And at this surface, whatever the conduction that is going in, Q conduction that is entering here, and then Q conduction that is coming out here. That is Q conduction 2. What is this boundary condition is saying is Q conduction 1 will be equal to Q conduction 2. And corresponding to this thickness, you will have Q conduction 1. Corresponding to this thickness, you will have conduction 2. So let me call this L1, let me call this L2. And here you have T1, here you have T2, here you have TA. So what you have here is the area is same for both the things. So effect of A can be taken out. K of 1, meaning K thermal conductivity of the material 1, thermal conductivity of the material 2. dt. What is this dt here? Here you can write that T1 minus TA by L1 you will have. On the other side, you will have K2 into TA minus T2 by L2. So this is how you will have yet surface A. So this will be your convection boundary condition. Okay. So these are all the 5 things in this 5. First 3 are very important, and you'll be using them a lot. So let me explain what is the use of this one. Okay. Let me explain the use of this one using this example itself. What is use of boundary condition? Let me explain that with a real-time example. Now, what I have drawn here is a wall. This is a wall of your room. Okay. This is wall of room. Any room you can take. If you take it, no, what happens is you will have a certain temperature T1 on one side and certain temperature T2 on the other side. Okay. So this is your thing. If I have to represent this particular heat transfer that is happening in this, what I have to do, I have to take governing equation. Okay. First thing in the process of defining a heat transfer problem mathematically is to take the governing equation in the first place. When I take the governing equation in the first place, what happens is, this is a rectangular coordinate system. Since this is a rectangular coordinate system, what it will be dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus q gen by k is equal to 1 by alpha into dt by dt. Small t I can take, small, some textbooks have tau. Anyways, so this is the thing, and this governing equation is representing the heat transfer in this phase. Now, if you look at this wall, will have temperature variation only in this direction, that is from inside to outside. Okay, this direction it will not have heat transfer. That is your vertical direction, that is y direction. So this can be neglected. Same way, in the direction perpendicular to this, that is z direction. In z direction also, the heat transfer will not be there. Internally, there is no chemical reaction happening in a wall or what do you call nuclear reaction. Anything of that sort is not happening. So this will be zero, and this will also be zero. This is more or less steady temperature. Okay, temperature on the wall is not varying with time. So only what you have here is dou square T by dou x square is equal to 0 is your governing equation. Now that you know governing equation, to solve any given governing equation, you should have something called as general solution. Okay, you should have a general solution. How do I get the general solution? To get the general solution, what you should do is you should integrate this one. Okay, take out this differentiation out of this. To take out the differentiation out of this, what I will do is I will integrate. When I integrate that, what I get is dou t by dou x is equal to C1, like I said. So this is what I will get. Basically, when I differentiate this one, no, I will get this. That's why when I integrate this one, I will get this. So reversal. Okay, differentiation. You'll get this. Integration, you'll get this. Okay. Now, this is the equation that you have here. Now, I want to further integrate it. When I integrate it, I have to take it like variable separable. Dou t is equal to C1 into dou x. If I do integration now, integral dt is t is equal to integral dx is x. So what I get is C1x. And since I'm not taking limits, I have to put one more constant here plus C2. So this will be your general solution. Okay. See, first what I have taken is first is my governing equation. In first place, to solve any heat transfer problem, you should have governing equation in the first place. This is the first thing. The next thing is general solution. Okay, when you do some integration, you'll get the general solution. This is your general solution. In this general solution, you have something called as arbitrary constants, C1 and C2. Okay, C1 and C2 are called as arbitrary constant. To solve this arbitrary constants, you have boundary condition. Okay, so that is what the use of your boundary condition is actually. So the boundary conditions will help you find out what is C1 and what is C2. Let us see this. Okay, this general solution you have, let me call this equation as 2, so that this equation is called 1. Now, let me take the boundary conditions. Okay, what will be the boundary conditions for this one? Here, this is x is equal to 0. Here, this is x is equal to L on the other side. Now, the boundary condition will be the temperature boundary condition or the Dirichlet boundary condition, which I can express it like yet x is equal to 0, the temperature is equal to T1. Yet x is equal to L, the temperature is equal to T2. Let me call this as 3, this as 4. Now what I will do is, I will take these boundary conditions and I will substitute into this equation 2. So let me take 3 in 3 in 2. If I do that, what I have is T1 is equal to C1 into 0 plus C2. So what it gives you is C2 is nothing but here T1. And then if I substitute 4 into what I get, T2 is equal to C1 into L plus C2 I will get. So this will be like T2 is equal to C1 into L. This C2 I can write as T1. So the C1 will be equal to T2 minus T1 by L. So now I got what is my arbitrary constant values. It is C2 and C1. So what I have is general solution T is equal to, in place of C1, I will write T2 minus T1 by L into X. Plus in place of C1, I will write T1. So this is nothing but T is equal to C1x plus T1. This is something like Y is equal to mx plus C. This should be C2 actually. Yeah, C1x plus C2. This is actually your Y is equal to mx plus C, a straight line equation representing a linear variation of the temperature. So in the case that you have taken, what you can understand from this equation is you can understand that the variation is linear temperature variation. Okay, this should also be written here. So the case taken, linear temperature variation is happening here. So this will be your general solution, wherein you will have the temperatures also into this equation. See, what is the use of your boundary conditions? The boundary conditions, they have converted your general solution of arbitrary constants into a real case. Okay, how it has created a real case, let me tell it with an example. The same wall boundary condition, wall case, wall. This is a wall case that we have taken, one-dimensional case. Let me draw this properly. This is why I'm putting it like this every time is it is representing the wall is infinite in this direction. This dimension is important to me, not this dimension. That is what the representation there. Now, inside you have 15 degrees centigrade. Outside you have 4 degrees centigrade. See, these are the values that I've taken from the problem that we have solved for the conduction case. Okay, 15 inside is there, 4 degrees centigrade is the outside temperature. This is the first problem that we have solved in our course actually. So the same problem I have taken it here, 15 degrees centigrade on one side and the 4 degrees centigrade on the other side. If this is the case, and the thickness is 1.4 that we have taken. Anything you can take. One example is important here. So now, look at this. I can substitute T2, T1, and L. This is T1, this is T2, and L is there. Now, if you look at this equation, I can transform it into like T minus T1 by T2 minus T1 is equal to X by L. Okay, this is a simple way of writing the same equation. Okay, see the beauty of this equation is this equation will help you find the temperature at any given x. Okay, temperature at any given x. At this x you know, at this x you know. In between you don't know. Okay, to find out the temperature in between, maybe at 1 meter you have to find, maybe one halfway you have to find 1/4 or 3/4, anywhere if you want to find, this equation will be helpful to you. How it will be helpful to you? Let us say at 1 meter, if I take, what will be the temperature at 1 meter? Temperature at 1 meter. I will write it like temperature at 1 meter. What is the value? If I want to find out, see, it will be like temperature at 1 meter minus T1 is 15 and T2 is 4 minus 15 is equal to Ex is 1 meter and the whole thing is 1.4. Everything can be substituted into it and I can find T1 meter. It is as simple as that. So what I'm doing is using a governing equation and a after a governing equation I've got a general solution. Converting this general solution into an useful solution using the boundary condition, I have got a real solution. Okay. So the thing is, in any heat transfer problem, the steps are this. You will have a governing equation. Once you have a governing equation, you can have a general solution. This general solution can be converted into a practical problem using boundary condition. Okay, these are the three things that you should keep in mind while solving any given heat transfer problem. First thing, along with this, we should see what is called as initial condition. Okay, initial condition is a special type of boundary condition which can be used for your transient problems. They're used for transient problems. So wherein time is involved. That is, there you have written at x is equal to 0, so and so you have written. Along with those things, here what you will have is yet time is equal to 0, meaning initially what is the case you are writing? Yet time is equal to 0, yet x is equal to 0, the temperature is equal to T1. That's how you write it. The same thing, you can write it the other boundary also. Yet x is equal to L, temperature is equal to T2. So that's what the initial condition is. So the thing is, this will be used for your transient case, that is your unsteady case, wherein your temperature is varying with respect to time, right? So that's what the use of your initial condition. So with this, I close first unit.